All right then, so yesterday's lecture was kind of important, and it seemed like lots of people were hanging around the tutorials quite a lot, and lots of people came back in the afternoon. The stuff we did yesterday is really important that you understand really well. So if you're still having trouble with that stoichiometry stuff that we did yesterday, then we may well have another tutorial on it again this afternoon, maybe including a little bit of what we're going to do today, but because today's is important as well. But that really the stuff we did yesterday underpins all the chemistry that you're going to see pretty much in any part of the course and in the first semester chemistry as well. This idea that you can take a mass and convert a mass of stuff into an amount of stuff and then relate the amounts of reactants to amounts of products in a chemical reaction is key to just about every calculation we can ask you to do. And at the end of the day, a lot of what we ask you to do in the exams and in the labs is calculations, right? And it's not ideal, but they're easiest to mark. We could make you write essays, but then you have to mark essays, and when there's 1,800 of the students, then that becomes a bit of a drama. So it's easier to ask you calculations, and that's what we tend to do. And so those calculations are always going to involve, somewhere along the line, you being able to do the stuff we did yesterday. So if that's still troubling you, then you should keep working at it. And if you want more help, then like I say, we might have a shoot this afternoon, or just come and see one of the guys over the way, or me, and I can happily make you up endless problems if you want more problems to try. Okay? So that was stoichiometry and amount is mass over molar mass and that sort of stuff. Today what we want to do is we want to start looking at some chemical reactions. We're going to look a little bit initially at something called dissolution reactions, and that's going to tie in quite nicely with what you're going to do in the lab this afternoon. But then we're going to go on and start looking at equilibrium. And equilibrium is one of these things which, again, is very fundamental from a conceptual point of view to a lot of the chemistry that you're going to learn this year, and is also one of the things that people find most confusing. So hopefully we're going to try and sort out some equilibrium stuff with you today. But first of all, we want to look at dissolution reactions. Dissolution reactions are reactions that you get with ionic compounds. So the ones we talked about the other day. Ones that are compounds which are made up of a cation and an anion, or some number of cations and some number of anions. And it's the reaction that happens when you take those ionic compounds and you put them in water. Because a property of an ionic compound is that when you put it in water, then it will dissolve. Now, as we'll see, it doesn't always dissolve completely, but it will dissolve to some extent or other. And when it does, you get back the cation and the anion that the compound is composed of. And so if we think about sodium chloride, then if we take sodium chloride and we put it in water, like you would if you were going to cook your potatoes and stuff, then the solid sodium chloride disappears. And you know that, you've done this. You put the white salt in and then there's no longer white salt there, it disappears. And that's because the salt dissolves to give you back the sodium cations and the chloride anions from which the sodium chloride solid was composed. And so we could write a little chemical equation like this. We write NaCl solid goes to Na plus aqueous. Remember, the AQ means that you've got the iron dissolved in water plus Cl minus aqueous. Would it be helpful if I had more lights on? How's that? Is that okay for the board? Yep. They rejig the room, but they still don't have these lights turned on with all the rest, so it still kind of works. Okay, so that's the equation that you would write for that process. Now, it is extremely important to note that nowhere in that chemical equation is there a water molecule. People do this all the time. They say, if you take the salt and you dissolve it in water, then that's NaCl plus water gives. It doesn't react with the water. It just dissolves in the water. Yeah? And that's very important that you understand the difference. Because what people do, and like I say, you see this all the time in labs, is that they'll write NaCl plus H2O gives. And then they'll go, well, hang on, I think it should be sodium plus and Cl minus, but I've got a water there, and that has to balance, so I have to have some oxygens. And so then all sorts of crazy molecules start appearing on the page. They make sodium hydroxide, and they make O2 gas, and they make ozone. And favorite one will be NaOHClH. Just stick everything together. Yeah? It's all wrong. There is no water in this equation. It reacts in the water. It doesn't react with the water. Yeah? Yeah.
Can we write H2O like above the arrow?
You could write H2O above the arrow if you wanted. Yeah? So sometimes you'll see this. And then you can write H2O like that. Yeah? When you write stuff above the arrow, that kind of talks about the conditions under which the reaction is happening. So that would imply this reaction is happening in water. But you don't write this over here as a reactant.
So that's peculiar to ionic equations.
Yes. Let's go with that. Yeah. When we come to do acid-base, sometimes that's different. But for these particular sorts of dissolution reactions, that is always the case. Yeah. Which isn't to say that some compounds don't react with water, but not ionic compounds. Yeah. Okay. When the sodium chloride dissolves, the bonds, and we haven't talked about what a bond is yet, but we're going to tomorrow, I think, the bonds which hold the sodium cations and the chloride anions together in the solid structure are broken and the ions are separated. Right? So in the solid, there's these interactions between the positive charge on the cations and the negative charges on the anions which enable the ions to stick together. When you put that in water, those interactions are overcome. And like I say, I think tomorrow we're going to talk about exactly how that works. But those interactions are broken, or those chemical bonds, if you like, are broken, and you make new ones between the cations and the anions and the water molecules. So the ions are separated, and we write Na plus and Cl minus with the AQ after it to show that the ions are floating around in aqueous solution. Right? So the ions are swimming in the water. They're not reacting with it. They're swimming in the water like fish. Yep.
Are they intramolecular bonds that are broken, or is that to do with something else?
Yes. Kind of. Kind of. If you consider your big lump of sodium chloride to be a single molecule, then yes.
Is it intra and inter?
Well, that's the thing, you see. It depends on how you define what the molecule is. I probably best leave those words alone for the moment. We'll come back to them as well. Now, this is a reaction that happens for all ionic solids. So if you're a solid that's made of a cation and an anion, this reaction will happen. And like I said before, it doesn't always completely happen, but it will happen to some extent or other. Other compounds will dissolve in water, but they won't undergo this sort of reaction because they're not ionic, right? So, for example, here, this is sugar again. We talked about sugar yesterday, C6H12O6. You know that if you put sugar in your tea or your coffee, then it dissolves as well. But it doesn't break up to give ions because sugar is a molecule that isn't made of cations and anions in the first place. Right? So then you want to say to me, well, how do I know if it's ionic or not? You'll know if it's ionic if you look at the formula and you can see in it things like sodiums and chlorides and fluorides and magnesiums and calciums. The sorts of things that you recognize that are in that table on the inside of your lab manual. Yeah? Normally, ionic compounds are made from a cation, which comes on the far left-hand side of the periodic table, and an anion, which are the things that come from the far right-hand side of the periodic table. Yeah? We talked about that the first day when we were doing electron configurations. This thing is all carbons and hydrogens and oxygens, right? Carbon's right in the middle. You can't get anions and cations and stuff with carbon, despite what some teachers tell you. So this isn't an ionic compound, so it won't dissociate in water. Okay? People are still writing? drink my coffee. We got that? Almost? No. Okay, so here's some to try. And note that it says remember to balance your equations, so have a go at writing some equations for those. Don't you do that in my big first year lecture. Then there'll be... Okay, so that first one, well, the first couple hopefully are relatively straightforward. It's just going to be potassium, K+, and Br- will be the cation and the anion that you form when you dissolve that one. For the second one, it's going to be lithium plus and Cl-. For the third one, calcium nitrate, calcium's calcium 2+. Remember, it's in the second row in, so it's a 2+ cation. So that means when you dissolve it, you're going to get one calcium out and 2 nitrates. We all didn't try breaking up the NO3 into some weird thing, did we? No? Right, remember, nitrate exists as an anion in itself, even though it's more than one atom. And then the final one, potassium carbonate, will dissolve to give you 2 lots of K+ and a CO3 2- anion. Right? It might be the first time... Oh, no, we had calcium carbonate yesterday, but this may be the first time you've seen carbonate. But again, it's in that... If you haven't met it before, it's in that table in your lab manual. And you're going to see carbonate, I think, in the lab this afternoon. So part of the lab, at least today, is going to be involved with doing some of these and writing equations. Yeah? Did we survive the lab yesterday? No one put pipettes through their hands yesterday? I didn't hear of anyone doing that. This is good. You've survived your first test. Okay. So that's ionic equations. And so they're relatively straightforward. They're far from the hardest equations you're going to learn how to do in the course of bridging chemistry. And I've already said this before, but we'll say it again. In many cases, when we add an ionic solid such as sodium chloride to water, it dissolves completely. All of the solid sodium chloride is gone, and only sodium cations and chloride anions remain. Right? So you take your salt and you stick it in water, and it all dissolves. And you can put more salt in, and you can stir it up, and it dissolves. And you can put an awful lot of salt in water before you can't dissolve anymore. Right? So pretty much, as soon as all the salt you stick in completely dissolves. And so we have this little phrase to describe that sort of reaction. We say that the reaction has gone to completion, because all the reactants have been turned into products. Okay? So if you like, here's our equation here, we say this reaction's gone to completion because all of this has turned into products. But the fact that I'm making a big deal about this reaction having gone to completion kind of implies that there's an option. And there is an option. The option is that the reaction goes for a while, but then it seems to stop. So we have reactions which do not go to completion. Instead, the reaction stops, or at least appears to stop, when there is still some reactants left, as well as some of the products which have been formed. And if that's the case, then we say that that reaction has reached equilibrium. And you find this happening with reactions of ionic compounds. You get some ionic compounds where they will dissolve, but not completely, regardless of how much water you stick in. And we're going to come back to those after morning tea, right? But for the moment, we're going to look a little bit at a reaction that doesn't involve ionic compounds, but which is incredibly unimaginative, because it's the one that we pretty much always talk about when we start talking about equilibrium. And it's this little reaction here, which involves a gas called NO2. NO2, if you've ever done, in fact, I think we're going to do this in one of the labs actually, where you take copper metal and you put nitric acid on it and you get those brown fumes all pouring out. Have we seen that? Yeah? If you haven't, Google it, it's cool. I'd do it in here, but it would contravene so many health and safety rules doing it in here that I probably shouldn't. But I think we do it in the lab at some point. So you make this brown gas called NO2, and under the right conditions, two of these NO2 molecules can combine together to make a bigger molecule called N2O4. Right? And so you can write a little equation like that. Two NO2s as a gas turn into N2O4, which is a gas. Now let's imagine that we have a flask which only contains NO2. Right? We've got some sort of glass container with a lid, and in it we've got some of this brown gas. We can change the conditions, and we can do this by heating it up or cooling it down or whatever, zapping it with electricity maybe. We can make this reaction happen. So we can start the NO2 turning into N2O4, but what we will find is that we are never able to turn all of the NO2 into N2O4. Regardless of how hard we try, we will never be able to make that reaction go to completion. What's going to happen instead is that under a particular set of conditions, the NO2 will turn into N2O4 for a while, but then it will stop. And it will seem like you can't make any more N2O4, and you can't use up any more NO2 in this reaction. So when the reaction has reached equilibrium, as we call it, there is no longer any overall change in the amounts of NO2 and N2O4. Yeah?
The reactions continue to go both ways?
Next sentence. Yes. The reaction forming N2O4 is still occurring, but what happens is you reach a point where the reaction going the other way happens at the same rate, or happens just as much as the reaction turning the reactants into products. And so we have two reactions going on. One where the NO2 turns into N2O4, but then at the same time, N2O4 is breaking up to make NO2 again. And so we have two competing reactions, if you like, one going one way and then the reaction going backwards. So overall, there's no change in how much of everything there is, but there are still reactions happening. And so that's given a fancy name. It's called dynamic equilibrium. And so maybe a good way to think about this, so dynamic equilibrium, there's another thing called static equilibrium. Static equilibrium is just when nothing's happening, right? So me just standing here is an example of static equilibrium. Dynamic equilibrium would be like if you were on, have we been to like these big airports where they have the travelators? Yeah? They're very cool. And so if you're on a travelator, and instead of just standing there and zooming along, or walking normally and feeling like you're sprinting down the corridor. If you're walking along on the one that's going the other way, yeah, then if you get this pace at which you're walking along at right, then overall you're not moving at all, right? If you've got someone standing beside you out on the carpet, then if you're walking this way at just at the same rate as the travelator's going back the other way, then you're not overall moving, yeah? You would think there was something on YouTube about this, but no, never mind. Maybe I have to make something just so I can use it and prove the point. So that would be an example of a dynamic equilibrium, right? Where you're moving forward, but the travelator's moving back, and when you're at equilibrium, you're moving forward at the same rate as the travelator's moving back, so overall you're not going anywhere. So that's kind of the same as your mate who's standing beside you just off the travelator not doing anything. That's like static equilibrium. They're not doing anything at all, but they're not moving. Whereas you're moving, but the thing's moving in the opposite direction, and those two movements cancel out. So that would be dynamic equilibrium. Yeah? You get that? No? So that's kind of what's happening with the chemical reactions. Initially, the NO2 is turning into N2O4. So if you like, you initially get on the travelator facing the wrong way, and you start going backwards, right? But then as you go along, as the N2O4 starts being formed, some of that starts turning back into NO2, right? And so then that's you starting to walk the other way. Still going backwards, but not going backwards quite as fast because you're starting to walk this way. And as the reaction goes further and more N2O4 is made, so more and more N2O4 starts reacting and turning back into NO2. So that's like you're walking a bit faster, and then eventually you reach equilibrium where you're walking forward at the same rate that the travelator is going back, and that's when those two reactions are going at the same speed. Does that make sense? Yeah? And so you reach equilibrium, and there's no longer any overall change. So if you were sort of looking through a window just as to your head and your mate's head, they wouldn't be able to tell necessarily that you were on the travelator and they weren't. Right? It would appear the same. There would appear to be no overall change. But you're undergoing a dynamic equilibrium, whereas the other person's a static equilibrium. Yeah? Have I pushed that analogy enough now? Yeah? Cool. When we get to equilibrium, the forward reaction, NO2 going to N2O4, and the backwards reaction, N2O4 going to NO2, are happening at the same rate. Both reactions are happening, and so what we do is instead of writing an arrow like we might write here for a reaction that's going to completion, we have this different sort of arrow that we write to describe this process, which is a double-headed arrow which indicates that the reaction is going left to right and right to left at the same time. Right? And so we write NO, so we would read that as being two NO2s in equilibrium with N2O4. Seems to me, oh, hello.
Is there any way you can indicate like what the major product is? Because you could have like lots of NO2 and just a little bit of N2O4 around.
You could do this. Yep. Sometimes you'll see things like this. And that would imply that when it reaches equilibrium, you have more of this than of that, rather than there being equal amounts. We're just about to get into the fact that sometimes you'd have more of one thing and less of the other. I'm not going to do arrows like that hardly at all, because these symbols don't exist on the computer. Yeah? But you do see it sometimes, right? And so that's how you would do that. I'm just thinking I should apply for some money. There's a beautiful travelator in the airport in Hong Kong, I remember from last year. Maybe I should get money to go to Hong Kong just to film so I can have it for lectures. You know?